Now I want to introduce this L'Hopital's rule. So you know that, right? So I hope you all know that. But now let's review. Right? Here, in order to calculate it rigorously, we need to use this L'Hopital's rule. Let me review it. Right. Method 2, now we use L'Hopital's rule to calculate the limits. Limit of ratio. When we calculate limit of ratio of two functions, based on the L'Hopital's rule, we can calculate limit of ratio of two derivatives. That's the key point, the power. So you will see, using this way, we can solve many difficult limit problems. So let's see. But there is some condition we need to check before we apply L'Hopital's rule. You cannot apply any time when you have the ratio of two functions. You cannot. You need to check if the condition is right or not. So what condition you need to check? Indeterminate form. Only when you have an indeterminate form, you can apply L'Hopital's rule. So what is the indeterminate form? Infinity over infinity. That's indeterminate. You don't know what's that? Infinity over infinity, right? Anything is possible. That's the indeterminate form. Another 0 over 0. Okay? That means when n goes to infinity, the numerator approaches to infinity, or denominator also approaches to infinity. Or 0, also 0. Okay? Yeah. So it's not a real. This is the form. Okay? We use this simple way as the form. Do not tell me, oh, this is illegal. Okay? Oh, that is illegal. Okay? Here we use that as the form. Okay? It's not we want to calculate what's that now. No. We don't want to calculate what's that. It tells us a special form. Okay? All right. Now, check. Is this an indeterminate form? Indeterminate form. Infinity over infinity. Yeah? Because when u goes to infinity, both infinity goes to infinity. Okay? So no problem. We can apply L'Hopital's rule. All right. Take derivative. Use derivative equals 1, right? I hope you know that. Very simple. Exponential functions derivative. There is formula. Yeah, there is a formula. Here we use that formula. Natural log of a is a positive number. Okay, then times the same function. Okay. So as I said, I will list all the formulas in the sheet and give it to you. Okay, this formula should also be included. Okay, all the formulas. If I find it in this class, I will put them together. I will collect. That is a formula we need to collect. Then, now, this time, it's not an indeterminate form, right? It's determined 1. It's determined, it's not infinity, it's not a 0. So you cannot apply L'Hopital's rule another time. It's illegal, okay? But now you don't need a L'Hopital's rule. Constant, constant, infinity. So the answer is infinite. Okay? So that's the first way we calculate. Why it is infinity. Another way. So here, let me calculate another time. This time, yeah, just remind you, be greater than 1. Okay? Another way, let's do not use the substitution expression. Let's calculate the limit on the original expression directly. Because when we use L'Hopital's rule, we do not need to do variable substitution, right? No. We can apply L'Hopital's rule on the original fraction immediately. All right, so here, let me show you how to do it. But here, before you apply it, I want to remind you of an important point. Discrete variable. Here, our n is a discrete variable. So do you know what is a discrete variable? Its value takes discrete values, 1, 2, 3, 4. That's discrete values, right? It's not continuous value. You cannot take 1.1. You cannot take square root of 2. You cannot take pi, because our n, that's the size of the array, can only be non-negative integer, right? 0 empty array, that's the size 0. Okay? We allow special case. So non-negative integer. So it is not a continuous function. It's discrete function, not continuous function. Okay? In that situation, you cannot take derivatives on discrete functions. Okay? You can only take derivatives for functions using continuous variables. Continuous functions, not discrete functions. That's why you should be really careful. Okay? Unfortunately, our textbook at this point applies L'Hopital's rule derivatives on discrete functions directly. So that's not a rigorous math. Okay? If you read textbook, you will find it. Apply L'Hopital's rule, but it's not a rigorous math. Okay? So be careful. So here, we want to do rigorous math. Okay? So how do we do it? We replace discrete variable by continuous variable. X, this time we take this form. Our x can take continuous values, okay? From certain positive number to infinity, but changes continuously. Not discrete values, jumping, okay? Changing continuously. This time, we can take derivatives. All right, now we are safe to take a derivative of x, 1, derivative of log x based on the formula 1 over the denominator natural log of a times x. Another formula, derivative formula. Okay? With that formula, after simplification, when you simplify, we get this. When n goes to infinity, this function goes to infinity. Okay? All right. If that function goes to infinity, when that function, the whole function goes to infinity, at the end, we can select discrete values go to infinity, right? Because for continuous value, this go to infinity. Discrete value is just the special values of those continuous functions. Like we can take a discrete value 1, 2, 3. Then we are safe. We know discrete values, continuous values, the fraction goes to infinity. But let's look at the special values at the discrete points, integer points. Also goes to infinity. Okay? So if you understand the limit, what's the limit? In any way you approach it to infinity, it should be infinity. That's the limit definition. Okay? Using any way you go to infinity. Here we use a special way, discrete points. Positive integer points still goes to infinity, right? So that's the definition of the limit. Anyway, you just go to infinity. Okay? You can go 1.5, 2.5, 3.5. That way to go to, you still get this limit. Okay? But let's take 1, 2, 3, 4, 5 to infinity. Let's get that limit. Okay? So in this way, we can prove it is infinite. Okay? After this proof, we can show people the growth function, this growth function grows faster than this growth function. Okay? Or in other words, the algorithm with this growth function is faster than the algorithm with this growth function. All right. So our conclusion. Now we can say that. Okay. Conclusion. The algorithm with growth function n log n is faster than the one with growth function n squared. That's the math we need to do for this question. So here you can see another conclusion. So after this first conclusion about the growth function, the second conclusion, method 2 is better than method 1. So you can see sometimes, I do not say always, sometimes if we pay some investment cost to get our data organized, we can get the better overall performance. Yeah. Sometimes we can do it in that way. So that is a very important view in problem solving. So later we may have many chances doing in this way. Any question?
How did you, through that process, determine that n log n was better than n squared? Like, I know it's almost easy to understand, but through the limits and stuff, why are we concluding that n log n is better?
All right. N squared, remember we did cancellation.
Yeah.
Okay? If we do not do cancellation, n squared over n log n, its limit is infinity. Is it enough to say this one is better? The limit is infinity. Okay? Growth function n squared, if you take very large equal size n, eventually it will overwhelmingly bigger number than the lower one. Yep. That's enough, right? When n large enough, okay? And we do not need to say how large it is. We just know when it is large enough, this number will dominate. Okay? Dominate. Remember the dominance I explained last time? The dominance means the ratio infinity equals infinity. Okay? If it's infinity, infinity can be larger than any given number. Right? So, all right. Let me use another way. Okay? Let me use another way to convince you. Because when you talk about infinity, people sometimes may not have an idea about infinity. It's another usual number. Okay. All right. Let me tell you. After a certain number, okay, just some number, this n squared will be 10 times larger than n log n. Are you convinced? One is 10 times larger than the other one. Are you convinced the smaller one corresponds to a faster and 10-to-1 ratio? Yeah, right? But our infinity definitely much more than that 10, right? Much more than 100-to-1 ratio, right? Much more than 1 million-to-1 ratio, right? Much more than 1 billion-to-1 ratio, right? Yeah. Then, that's why we can comfortably say which one is faster, which one is slower. Okay? Because 10-to-1 ratio already enough to convince us. Okay? All right. So try to think in that way. Infinity can be any large number, can beat any large number, actually. Okay? Any large number you want, you can beat it. Okay? Good. Any other question? All right. Now let's move next unit.